Hi, everyone. So today we're very happy to have Antony Speranza visiting us from UIUC, just nearby. And he will be talking about complexity equal anything squared, plus some diffeomorphism stuff.
Yeah.
I'm pretty sure it's going to be a great talk. Please.
Okay. Okay, yeah, thanks a lot for the invitation and the chance to tell you about this work. Yeah, so the title is diffeomorphism, invariant observables, and holographic complexity, or the slogan is complexity equals anything squared. And yeah, this is some work that I did in these two papers with Alex Bellin, Rob Myers, Shanming Ruan, Gabor Sorosi. Okay, yeah, so one thing that I think is super interesting about holography is that it's really forced us to start thinking more deeply about diffeomorphism, invariant observables, and gravitational theories and what they mean in a sort of a quantum theory of gravity. So I'd say one of the best examples of this and sort of the things that we can learn about observables in gravity from input with the input from holography is this Ryutaki-Yanagi formula, which I think is fairly well known, but okay, so this is something about entanglement entropy in a dual CFT. So you have a subregion in a CFT. You're interested in computing the entanglement entropy, and the Ryutaki-Yanagi formula says it's equal to the area of this bulk surface, this minimal surface in the bulk dual geometry. And so just this connection between a geometrical quantity in the bulk and some sort of quantum information observable on the boundary has led to all sorts of insights on both sides. So it gives you this relation between gravity and quantum information, and it also gives this cool relation between geometry and entanglement, in this case entanglement entropy. For example, you can actually use this formula as the input, and as the output, you can show that the geometry has to solve Einstein's equation. So there was a number of interesting works showing how that relationship comes out of just assuming this formula. And you can then compute quantum corrections to this formula, and it tells you how to think about sort of the quantum corrected area. You replace it with something like a generalized entropy in a subregion, and it gives you an interpretation of the generalized entropy in terms of actual entropy of degrees of freedom in the CFT. And this has led to all sorts of insights about the black hole information problem and black hole evaporation, such as the recent work on islands and quantum extremal surfaces. So that's all great, but there's some situations where, even though entanglement entropy and minimal surfaces are super interesting, there's some situations where they're sort of not probing some aspect of the geometry. So the standard example is in the setup of like the thermal field double. If you want to say something about things behind the horizon, it's kind of hard to do that with minimal surfaces, just for the reason that they kind of tend to avoid the interior of the black hole. On the other hand, there's just clearly all sorts of geometry going on behind there. So if you really believe in some sort of geometry from entanglement or something, there should be a way of writing down something in the CFT that's telling you about the stuff inside the horizon. So the standard example of a thing that's interesting in this thermal field double is the Einstein-Rosen bridge, where if you're in the thermal field double and you evolve forward in time on both sides, you eventually are going to get this maximal volume surface that's going to continue to grow for infinitely long times in the classical theory. So it'll just continue to get longer and longer as you evolve upwards. There's a question of what is that supposed to be dual to in the CFT, since this grows for time scales much longer than any sort of thermal time scale that you would write down in the CFT. And this is sort of the motivation for the proposal that perhaps something about complexity of the quantum state is being measured by this this Einstein-Rosen bridge. So yeah, so yes.
It's a silly question.
Yeah.
If we're feel free to respond later. If we were dealing with de Sitter or something, are there any diff-invariant thing you could have written?
Yeah, de Sitter is a little tricky because when it comes to diff-invariant things, you usually do some sort of dressing. And in that case, there's not really an asymptotic boundary to dress to. They're sort of future and past boundaries.
I guess I was asking, is there any way to get diff-invariant stuff without anchoring to the boundary?
So a lot of people would say no. Maybe I could tell you towards the end of the talk, maybe I can tell you about some of the things that I'm going to introduce that seems like I could write something down that looks like it's not really boundary anchored in any sense. So I think, it's interesting. There's always a question of like, okay, did you really write something down that's sitting in the bulk, or are you secretly, anchoring one point to the boundary? So that's worth thinking about, and that's definitely relevant in de Sitter, where some claims are that there's kind of no algebra in de Sitter, and you have to add something to get a non-trivial algebra.
Okay.
Yeah, but yeah, I'll try to maybe if it doesn't come up again, just remind me. I'll try to point out something like that. Okay, so the idea is that maybe it's something to do with the complexity of the quantum state in the CFT. So I have to tell you what I mean by that. So this quantum state complexity, this is sort of motivated from considerations of computational complexity, and it's defined as the minimal number of simple gates that you need to transform a reference state, which we call psi 0, which is like your simple state, into the state that you're talking about within a tolerance epsilon. So you would say that I want to construct some unitary that is a product of simple unitaries that I call S sub I. And I want to construct this unitary so that this state is close enough, within epsilon of my reference state. So acting on the reference state, I get to my desired state. And then I define the complexity as the smallest circuit that I need in order to get within this tolerance epsilon.
I have a basic question. How do you pick reference state?
Okay, so there are clearly ambiguities in this construction. So the question is, how do you pick the reference state? Okay, that's a choice that you can make. And there's also clearly a simple gates. I have to tell you what those are. And it's basically your complexity is going to depend on these choices. And usually the way it works is that in complexity theory, I guess people are more interested in universal scaling properties as opposed to the actual value, because of course I could always pick my reference state to be my state, and then the complexity is 0 in that state. But you're really interested in how various things are scaling over, say, the whole Hilbert space. But of course, there are certain ambiguities in the definition, and maybe if you're trying to propose that it's dual to something unambiguous in the bulk, you might be a bit worried about that something. So yeah, so from the bulk perspective, the original proposal is that, okay, it's just one thing, it's the maximal volume slice. That's unambiguous. And you could ask, okay, what exactly is singling out the volume in this construction? So for one thing, it's like, okay, we'd say the volume for Einstein gravity, but in certain contexts, you say I have a higher curvature theory. We know, for example, that if you're doing the RT formula, there's going to be corrections to the entropy functional. You might expect that that the volume ought to also get corrected. And there was a proposal that we made a while ago in a kind of different context, but we found something that looked like a higher curvature generalization of a volume. And this was sort of also derived in sort of a Randall-Sundrum like construction where they were looking for a higher curvature complexity. And so you can see that the natural generalization of the volume tends to receive higher curvature corrections. The other point is, though, there's things besides the volume of the slice that probe the geometry behind the horizon. There's all sorts of things that I could write down on slices that penetrate the horizon, and those ought to, have similar universal properties that you might expect with complexity. And there's just like a general question of, you know, that there are these ambiguities here, but there's not one here. So how do you come up with bulk observables that reflect this inherent ambiguity of the complexity? Okay, and then, you know, after the volume was proposed, there were some other proposals as well. So maybe it's action. This would be something that's actually sensitive to the type of gravitational theory you have. Maybe it's something like space-time volume. And there's maybe was some debate of which one's better, or how should I interpret these different functionals. Okay. But even the go ahead.
The other side of the coin, are there other proposals for what the volume is? If it's not the complexity, what is the other proposal for that?
In terms of like a thing, if it's not complexity.
The complexity could be different things in the bulk, but in the bulk you still have the volume. And if you say volume is not complexity, then it has to be something else. Is there any proposal for?
I would say it's probably a measure of complexity. And so I'm not saying that it's not, I'm saying that there are other measures of complexity as well. Yeah, and then, yeah, in some sense, it's just a thing that is sensitive to, you know, whether or not the state is complex. And at the end of the day, the volume is kind of an observable. So it's like an operator, which the complexity is maybe not so much that. But it's something that's sensitive to the fact that your state is becoming complex for long times. Okay, but the point is, even though there's these three proposals, that doesn't reflect the kind of infinite degeneracy of ambiguities in this choice of states and gates for the complexity of the CFT. So the goal of this talk will basically be to introduce a broad class of diff-invariant observables in the bulk and claim that, you know, these are all good measures of holographic complexity and that they at least satisfy the initial tests that you would want them to satisfy. Okay, so in the process, there's kind of two sides of what's going on in the bulk. We just want to talk a bit more about how you actually construct diff-invariant observables, and I think we have sort of an interesting proposal for kind of a broad class of what I'll call relational observables that implement diff invariance in a kind of nice way. And I want to further kind of develop what these observables are doing by showing that you can actually compute their algebra on the classical gravitational phase space using this Peierls bracket construction. And there's certain really interesting things that come out of this Peierls bracket construction related to extremality conditions. So in particular, if you recall, we were talking about the maximal volume slice, and we'll see that that kind of comes out naturally from this construction. And so then once I've introduced these, I want to show you that at least these, you know, broadly kind of anything that you write down satisfies these two basic properties, is that they exhibit this linear growth for infinite time in these thermal backgrounds. And so that's infinite is classical. And so in quantum mechanics, it would be exponentially long times. And then also claim that they satisfy this switchback effect, which was a check that these are complexity measures. Yeah. So,
but you're going to talk about these functionals that depend on this particular RT surface that goes between the two, right? So,
well, they'll depend on the surface that's determined in a specific way.
So I'm asking, is this equivalent to choosing a D-1 form on this surface that you want to integrate?
Yeah, that's the thing that you want to, yeah, that's.
And then you would have thought, well, that action would give you a functional like that, but here is not the case because you don't have a global time like Killinger along the surface, right?
Sorry, what?
So Lagrangian is a D form.
Oh yeah, and actually okay, I mean in this talk I'm going to focus on codimension 1 things, but the new paper also showed that, you know, even these things like action and space-time volume are top forms, so those are codimension 0 things. And the argument was, okay, also I'll be talking about some things like action that are codimension 0, say. So yeah. Okay, I don't know if you're asking something else. Okay.
Yeah, we'll talk about it.
Okay, so that's kind of the general plan of what I wanted to get to today. And so, yeah, the thing I want to start it with, and sort of, if you know me very well, you'd probably know this is why I'm most interested in these things. I'm kind of first a gravity person, and so I really like thinking about diff invariance and its consequences in gravity theories. So what does diff invariance mean? Well, okay, diffeomorphisms are gauge symmetries in gravity, which means if you have a good observable, they should be invariant under diffeomorphism transformations. In the canonical setup where you do the 3+1 or the D+1 split and write down, the phase space in terms of momenta and the the momenta and the metric on the a Cauchy surface, that means that any functional you write down as an observable has to Poisson commute with the constraints, which are the things that are generating diffeomorphisms. So you have here the momentum constraint and the Hamiltonian constraint. And these guys are kind of on different statuses. Roughly, basically, the momentum constraint is kind of the easy one to deal with. This Poisson commuting just means that you wrote down something that looks covariant on the surface. So you wrote down something that looks diff invariant when constructed out of Hij and Piij. So you do the usual thing, you use covariant derivatives and curvatures, contract everything nicely, and that's gonna Poisson commute with the momentum constraints. The Hamiltonian constraint is actually a bit trickier because there'll be things that you write down that look nice when expressed in H and pi, but will not Poisson commute with the Hamiltonian constraint. So you have to think a little bit about that. So it's kind of easiest to see with an example. So this came up in this New York Times paper by Bellin, Lukowitz, Sorosi. So they were thinking about complexity, but they also were one of the first ones to focus on kind of connecting complexity to this canonical stuff. And they said, okay, say you write down just the volume on a given Cauchy slice, and I haven't told you anything about that Cauchy slice. So this thing clearly looks like it's diff invariant in terms of the spatial diffeos. That's just a nice functional constructed just out of the induced metric on the surface. That's going to Poisson commute with the momentum constraints. And so then they said, okay, compute the Poisson bracket of this thing with that Hamiltonian constraint. There was some sort of extrinsic curvatures there. You see, this is a function just of H, and then this part right here are pi's. So you're going to get some non-trivial bracket here, and it basically generates an extrinsic curvature integrated over the surface. And so you see, it only commutes if the extrinsic curvature of that surface embedded in spacetime is in 0. So that means when you try to write down the volume of the slice, the diff invariance is saying that you really meant to write down the maximal volume slice. So you're imposing k = 0 as kind of an equation of motion.
Antony?
About it for a little bit, you'll see why this is happening. Really, the Hamiltonian constraint is basically generating surface deformations. And so what this is saying is that you've written down a surface that at first order doesn't change under a surface deformation. That's just the extremality condition. So you can ask, is that really, that argument should suggest that this is going to occur more generally, that you're always going to extremize your observable. And so, yeah, so that's what that question is. And the answer is going to be yes. But there's kind of a nice way to see how that happens. So, yeah.
There could be several maximal volume slices, right? Is that possible?
In principle, yes. There are kind of arguments, at least in ADS, that maximal volume slices are unique, but it requires, thinking of it. Yeah, there's these global arguments that that's true, and it might not be true in certain backgrounds or
but
other.
ADS to believe it's true.
Yeah, so there was this talk by Witten at this 20 years of ADS CFT conference where he essentially sketched the proof, and then it never ended up in a paper. So I'm assuming there was some math thing that was more complicated, but you know, at the level that you and I should be concerned, it looked like a pretty solid proof. So, but yeah, there's certainly situations where there might be multiple extrema, and you could ask what's going on there. Like, in principle, you could always, you know, around a given background, you could say, okay, these two extrema are kind of separated by a finite amount, and so you would expect I can pick one or the other, or just say I want to go to the actual maximum, and possibly the other ones have non-perturbative effects when you're computing.
It opens up your room for phase transitions and stuff.
Yeah, for example, yeah. Yeah, so I mean, there will be situations when you write, I think generically, if you write down more complicated things, it's easy to get multiple extrema, but at the very least, you can say just go to the maximum one. So in order to kind of prove this more generally, we found it useful to, instead of using this canonical, you know, pi and hij construction, it's kind of useful to use this Peierls bracket construction. So this is a thing that's closely tied to the covariant phase space. If you're familiar with that, it's sort of a way of trying to do the phase space of GR without doing the 3+1 split. And so the Peierls bracket, so the covariant phase space is sort of giving you a symplectic form, and then the Peierls bracket construction is basically how to do the Poisson brackets in that sort of setup. And so,
is there a way to think about this as some sort of center of the algebra of functions on the phase space that you mod out by?
what's the center, or what's
it commutes with all the functions on the phase space?
Right.
So there's the algebra of functions in the phase space.
Well, it commutes with the constraints. So there's a in the canonical picture, there's a phase space there that diffeomorphisms act on, and you have to restrict to the zero constraint surface, and you have to mod out by the action of the constraint. So this is this. I think this. It's not Dirac. I mean, I think it is Dirac, but I don't know. The what is it called? It's Hamiltonian reduction, symplectic reduction, something like that. This Marsden-Weinstein thing. Anyways, there's a fancy math story there. But yeah, it doesn't commute with.
But K commutes with all the F's, or H commutes with all the F's. So it's like an outer. You have the center. It's an outer transformation.
Yeah, I mean, you have a big space where the group of symmetries are acting, and you're trying to go to the invariant space under that action. Yeah. So yeah. So I mean, it's not central because these things don't commute with each other, right? So
yeah.
Okay, so yeah, I was going to briefly introduce the idea behind the Peierls bracket construction, just so you can get a flavor of how it works. So the idea is, so say you have some observable f, that's some functional. You can think of it as being evaluated on a codimension 1 surface, or it could be integrated over all space-time. So you just have some arbitrary thing that you write down, and you want to try to construct the transformation that operator is generating on your phase space. So I want to say phi here are my dynamical fields. You can think of that as the space-time metric. And I want to determine an infinitesimal change of those fields that is generated by this observable f. So the Peierls construction says, okay, you sort of add this operator f as like a source in your action. And so you have this parameter lambda. And you then, once you've added this as a source, you get these deformed equations of motion, and you want to solve these deformed equations of motion to first order, where now you have this sourced term here. So you're solving these linearized source equations of motion. You want to look for both advanced and retarded solutions to first order in lambda. So that's, you sort of think of f as being at least localized in time. The advanced solution, yeah, so the retarded solution will kind of agree with the background to the rest of the insertion, and then you insert the operator and it does something, and then the retarded solution, it agrees in the future, and inserting the operator changes it in the past. And so those are both solutions to the sourced equation. So their difference is going to be a solution to the source-free equation of motion. And that difference, since it's a solution to the linearized equation, it actually defines a valid transformation on your covariant phase space, which is the space of all solutions to your equations of motion. So an infinitesimal change in your solution is a linearized solution. And that's this advanced minus retarded solution. And you can show that if you stick this into the symplectic form that you would construct by this covariant phase space methods, that it actually gives you the variation of f. This is just Hamilton's equation of motion for that transformation. So that tells you that this infinitesimal transformation is the one that you were looking for to be generated by this observable f. And so in particular, that means the Poisson bracket of f with some other operator g is just given by variation of that with respect to g times that variation there. So that's just the action of this infinitesimal transformation on g. Okay, so that's sort of just a brief review of how this Peierls bracket construction works. You should kind of think of this as just taking the classical limit of a sort of the same construction of in the path integral, where this should be familiar, where you write down sources in the path integral and you sort of take derivatives with respect to the source to get correlation functions. Yeah, and the point is it's sort of covariant because you're doing everything at the level of the action and equations of motion. You haven't given me a slice or anything like that. Okay, so the reason I went through all of that is that you can actually use this Peierls bracket construction to show that anything you stick into this construction is going to be different. So what does that actually mean? So say I on the previous slide, I mean, nothing I did required f to be diff invariant. I'm allowed to stick anything I want into an action and compute equations of motion. So let's just assume we stuck something that really wasn't diff invariant. It depends on an arbitrary surface in space-time. I haven't told you how it's embedded in there. And let's just try to, go through that construction and see what comes out. So what you can do is you can say, okay, let's take some scalar functions that at least describe how this function f is embedded into your space-time. And if I took f to be a functional of the dynamical fields and x, now it's going to be diff invariant because, okay, you can kind of absorb all the non-invariance into transformations of these x embedding fields that just tell you where the thing is. On the other hand, because these x's aren't actually fields in the theory, so the thing still isn't diff invariant because these we're not going to actually vary the x's in like computing equations of motion. However, so the x's are not dynamical, so you don't impose the equations of motion. However, this thing as a functional of the dynamical fields and x just is diff invariant. So that means if I did a diffeo on this s, it would be 0 up to boundary terms. On the other hand, if I do a diffeo, that's going to look like the variation of this action with respect to phi times the Lie derivative of phi plus the variation of the action with respect to x times the Lie derivative of x. That's just what that variation is. And so on shell, this thing is 0. And because the total action is diff invariant, the whole left-hand side is 0. And so the fact that the original action was diff invariant actually enforces the equations of motion in this construction for f. So basically what happens is that your equations of motion had some diff symmetry. And when you stick this non-diff invariant thing in there, it sort of uses some of the diff symmetry to ensure that the operator you inserted is actually extremized. And that's actually one of your equations of motion. So the point is you're always going to get the extremality condition for a functional f when you use this Peierls construction. So it's kind of a nice feature. But using the Peierls construction, it's going to extremize anything for you. And then it's telling you, okay, the thing that you meant to stick in there was the diff invariant thing. And again, this is just like when we did the volume construction. In the canonical case, we found that commuting with the constraints is that this functional is extremized with respect to the embedding field. So if F was the volume and then this is just the embedding of where the surface is, you would say this is essentially the Hamiltonian constraint for you there. Okay, so that was one of the neat outcomes of this, is that this Peierls construction is useful for getting diffinvariant functionals. Okay, so then that's nice, but you could also complain that you could just think of things quite easily that aren't just something that's extremized on the surface. And so that's this generalization that I wanted to talk about, is that what I could call relational observables, which we'll call F12. And what that is you're going to take a functional F1, so say it's some density W as a function of H and pi, evaluated on a surface, but the surface that we evaluated on is not the extremal surface for this functional, it's the extremal surface for a different functional. So we pick the surface using one functional, and then we can evaluate any other functional on that surface. That should still be diffinvariant. Right, yeah, so we evaluate, yeah, we extremize F2 and then evaluate this F1 on that surface. So you could ask, okay, how does this thing appear in the Peierls construction? And this is something you can work out as well. You can form this combined functional where you take the sum of both F1 and F2, where you have an extra parameter epsilon in front of F1, which is the thing we eventually want to evaluate on the surface. So this functional here in the Peierls construction will always be extremized for each value of epsilon. And so as epsilon goes to 0, the surface you're evaluating it on is just extremizing F2. If you take the derivative of this thing with respect to epsilon, because at each value of epsilon, the thing is extremized, you're not going to get any contribution coming from moving the surface, because at first order, there's no contribution there. So you're only going to, the derivative is only going to hit the epsilon appearing explicitly here. And that's going to just say, okay, you're evaluating F1 on the surface sigma epsilon. So then if you take epsilon to 0, you're evaluating F1 on the surface that extremizes F2. So this is a way to see how you can get these relational observables from this family, kind of doing a family of extremized functionals here. Okay, so now this kind of opens up an incredibly broad class of observables. You sort of have a doubly infinite class of things that you can do in order to write down diffinvariant observables on Cauchy slices or codimension 0 subregions as well. Okay, so yeah, it's useful to consider an example. This is going to be a codimension 0 example. So you could take F2, the thing that we're going to extremize, to be the following combination. So you'll have some subregion bounded by two surfaces, sigma plus and sigma minus. We can write down the volume in between those surfaces, and then plus the volume on sigma plus and the volume on sigma minus with these coefficients alpha that are, I mean, at the very least, they're required sort of by dimensional arguments there. So what is the, what happens when you extremize this functional? So that looks like this. You can just work out the equations of motion for extremizing this functional, and you find that these surfaces have to be located they're located as being constant mean curvature surfaces. So instead of k equals 0, you have k goes like plus or minus 1 over alpha. So you get these kind of lens-like looking subregions. And so you can tune the values of alpha plus and alpha minus in order to get different shaped surfaces using this kind of construction.
So the boundary, you didn't have to meet at the same point in the boundary, right? You could shift this from global time and ADS. Like on the boundary. Right?
Yeah, I guess that's a boundary condition. I guess we're picking it like this because as you'll see, we're kind of going for the Wheeler to it. Yeah. Yeah, so yeah, okay, that's true. You could in principle let that be free, and then you would have to come up with a way of picking that separation as well. So now if I just take my F1 to be the action for this subregion, so I'd have the bulk Einstein-Hilbert plus cosmological constant term, plus some Gibbons-Hawking terms on the future and past. Now I'm going to get, so what is this observable? I'm getting the action of this subregion. And so I use this F2 to determine the subregion, and then I wrote down F1 as the action of the subregion. So now what you can do is you can take this null limit. So if you take these parameters, alpha plus and minus to 0, so the extrinsic curvature was 1 over alpha. So this is going to cause your k's to go to plus or minus infinity. All that means is you're just sort of pushing these surfaces towards the light cones. So what happens in this limit is you're approaching this Wheeler-DeWitt patch, so where the boundary of the surfaces are becoming null. So that's again extremizing the F1 functional, which was just, or the F2 functional, sorry, which was that top object. So in this limit, you get the region of consideration as your Wheeler-DeWitt patch. And so now if you just pick F1 to be the subregion action, you're going to get the action of the Wheeler-DeWitt patch, which of course is one of the proposals for complexity measure.
So is there some sort of simple way of describing what that functional we started with was? So volume plus the volume of the
And I'm just adding like volume of the top surface, volume of the bottom surface, and volume in between. And there's just coefficients for the top and volume, bottom volume.
The limit is 0. When you take the limit of these coefficients going 0.
Yeah, you kind of have to take the limit, because if I don't write down those top and bottom things, you could ask, okay, where the volume of what, the whole space-time, or what am I doing? So yeah, you kind of, I'm not exactly sure how to write it down directly other than from this limiting procedure, because I kind of need to at least have a subregion.
I understand, I'm just saying that, yeah. Okay.
But yeah, I mean, alpha plus and minus goes to 0. So yeah, so these things are just 0 in that limit, these terms.
So the extremely curvatures are blowing up.
Yeah, so they blow up, and so you can think you're bending the way up towards the light cone.
Right,
yeah,
because it's like making this.
Yeah, okay, yeah. If it was a causal diamond, you're going towards the tip. Yeah.
Right.
Yeah.
Naive question, but I think in the early days of LDSFT, the idea was that if you do coordinate transformation in the bulk, you change the metric, and the boundary metric changes by a right factor, but because it's a conformal theory, it's okay. So these are sort of conformal invariance in the boundary, or right invariance, or you are keeping the boundary metric fixed.
Yeah, I think we're probably restricting to diffeos that are fixing there, so that you would get you get the Weil factor if the diffeos have like a certain fall off of the radial component, right? And I think
these are large diffeomorphisms, right? These are small. These are actual diffeomorphisms.
These are the ones that are actually gauge, and for like those ones are things that would have non-trivial charges. I think those would be diffeos that.
Can you use that for these methods also for those to find?
Well, I would just say you don't necessarily need your observables to be invariant under those diffeos, right? Because those are the ones that actually have non-zero charges. On the other hand, yeah, you can write these things down. So basically, this is all about the diffeos that aren't acting near the boundary and trying to ensure invariance under those.
So in the boundary, you don't have any invariance. The dual quantity is not invariant under anything. In this
it's not like it's not necessarily invariant under like the conformal group, I guess. Yeah, it could. You would expect it to be some operator. I think you would expect it to not be a very simple operator in the CFT. Usually these observables that kind of connect both sides are generally fairly complicated CFT objects, and maybe there's not such an explicit thing that people have written down in the CFT. Okay, yeah, hopefully that makes sense there. Yeah, and so okay, there's something else that this is somewhat of an aside on this story, but I think it's super interesting and maybe not so well known. Here it's kind of interesting that actually you can take this null limit of the action. So in principle, you could just say, okay, extremize this F2, take the limit, and then write down the action with null boundaries. But the other thing you could do is just say, okay, write down the action with the two space-like boundaries and try to take this limit where you take these, you know, these surfaces to approach the light cone here. And it's a bit surprising, but this given talking term that you write down actually has a finite null limit. And there's some kind of interesting things that come out of that. So what's going on is, okay, when you take this null limit, this extrinsic curvature is diverging. That was the K going like 1 over alpha. But on the other hand, your surface is becoming null. So this induced volume form is going to 0. And they actually, those divergences are exactly opposite, so that this thing is actually finite when you take that limit. And what you can show is that as you take this null limit, you get the standard null boundary terms in the gravitational action, which were written down like not so recent, or yeah, in the not too distant past. So sometime in the teens, people actually discovered what this null boundary action was. So just to describe what this is the expansion of your null surface, and then these kappas are surface gravity-like quantities. Anytime you have a null surface that's not a Killing horizon, there's a bunch of different definitions of surface gravities that in principle all disagree, so you have to be a little careful. But essentially these two terms are the ones that you naturally write down for the action with a null boundary. This kappa 2 is the failure of your null generator to be affinely parameterized, and these kappa 3 and kappa 1 are some other notions of surface gravity that I can tell you about if you're interested. But so you see that the null limit exists and that you get a sort of modified action in this null limit.
So all of these K1, K2, K3 are things that we could measure as an observable near this null surface, right?
Yeah, the problem is, so kappa 3 and kappa, they all kind of depend on certain arbitrariness. So there's sort of a choice of scaling of kind of, there's no canonical normalization of the null vector, and rescaling it can change these. And kappa 1 and kappa 3 also depend on how you're approaching the null surface. So you need to pick a foliation.
Surface gravity in your horizon is very observable. It's not a.
Well, these all agree on Killing horizons. Yeah. So in that case, you have a Killing vector. It's normalized. It has a canonical normalization up to just a constant rescaling, which these guys don't depend so much on. Or, I mean, okay, the combination, the constant rescaling kind of is absorbed with this volume form as well. But yeah, on generic null surfaces, you have to be more careful, and there's various ambiguities. In this null limit that we're talking about, we've actually picked a foliation. We've told you you're doing the CMC foliation, and so all of these things are well defined, but they're maybe not so intuitive to compute, you know, or say generic things about.
Yeah, so this is calculated with particular choice of foliation in mind.
Yeah, that's the CMC. I mean, in particular, think of the CMC.
What is CMC?
Constant mean curvature slices. Okay. Yeah, sorry. Yeah. It's a little funny too on Killing horizons. All of these surface gravities agree, and they're constant on the Killing horizon, which is the 0th law. So you can see so this would cancel that, and this would be 0. So this would be 0, and then that's also 0 on a Killing horizon. I don't know what. Okay, so on Killing horizons, the boundary term is 0. But yeah, and so what this one side effect of this is that, okay, you have this Brown-York stress tensor that's normally defined on, say, a time-like boundary, or, okay, we were talking about space-like surfaces. I can write down a stress tensor-like object as well. These are essentially the momenta on this if you're doing a space-like surface. And that also admits a finite null limit as long as you put the indices in this combination with one up and one down, which becomes important when you're on a null surface because you can't raise and lower indices on null surfaces because your metric's not invertible. And so what happens in this null limit is you get what this term right here, which is essentially the Brown-York stress tensor that you would get using the standard variational principle with these two terms. That was something we looked at in this paper from last year. And then the null limit that's roughly generated by these guys, you get specific corrections where these A is something that's constructed from the gradients of these surface gravities appearing here. So it's kind of interesting that this null limit is finite here and that you can get this null Brown-York stress tensor as well in this. Yeah, maybe to say something else, when people talk about actions for subregions, they also are concerned about the contributions at codimension 2 corners. And there the story is a little more complicated. So that's this Hayward term is something that you would write down at when you write down the action with a codimension 2 corner like this. It's given by this expression here. This is essentially some kind of boost angle between the two surfaces that are intersecting. So this n plus and n minus are the time-like unit normals to the surfaces, and then this s is the space-like normal that's pointing, tangent to the top surface when you get to the codimension 2. And this thing's a little more complicated because it diverges in the null limit because these are unit normalized vectors, and as they all become null, you're sort of dividing by the norm, and so you're dividing by 0 there. Does that make sense? Anyways, yeah, S hat is some finite unnormalized guy divided by its norm, which is becoming null. However, you can show that the divergence coming from that dividing by the norm there is sort of constant. And so you can renormalize it in a certain sense by subtracting off some constant. And when you do that and you're careful to not affect the variational principle, you again get this term, which is the standard null joint term that was explored in this work, plus again, a correction involving surface gravities of the two null surfaces. Okay, so that's just a little aside talking about some of these null limits, which I think is kind of an interesting upshot of some of these investigations.
Are there any nice physical interpretation of the integral, these given starting null terms? I mean, in the standard story, we say these are related to charges and stuff.
Oh, like the relation to charges, you can use this stress tensor. Like if you want to write down, people talk a lot about charges on null surfaces, and you can construct them from this stress tensor here. In that case, I would normally just use this standard one here, and so that you can think about what's going on if I'm trying to take a null limit of charges versus just working directly on the null boundary. But yeah, whenever you have one of these Brown-York stress tensors, you just get the charge by plugging in the vector and integrating it. And you can show those are equivalent to charges that you would construct with some walled type thing.
What charges?
What's that?
What charges?
They're like I don't know, like quasi-local energy type charges. So if you plug in a time translation or the null translation, you're going to get the energy associated with that translation.
Is there like charges that correspond to deformations of the?
Yeah, just diffeos going up. If you plug in a rotation, you'll get an angular momentum, for example. So
In flat space holography, sometimes they talk about these charges super rotation super.
yeah, for example.
This is for this like the width thing from the top and bottom, right?
Wait, sorry.
These are for deformations of just the future. This upper part.
Oh yeah.
Lower part, right?
Yeah, well, I guess in flat space holography, you usually are out at scry and you're at a cut of like the top part, and then you're constructing things up there. Yeah.
In flat space holography, that's the case.
There's all sorts of things as well. I mean, like the Strominger group kind of does things differently sometimes as well. So there's maybe more spatial infinity, or I don't know, or something in between.
Well, I thought the Strominger group, as there's a group in mathematics.
No, the army of physicists.
Yeah.
The research group.
Yeah.
Okay, so finishing up with that aside, come to the title of the talk. Okay, so basically we've identified this broad class of different variant observables that I called F1, 2, where Yeah, well, the convention was, I think we extremize F2 and evaluate F1 on it. Okay, and we've also kind of in the process showed that these observables in special cases reduce to the three proposals for holographic complexity. So if you take F1 and F2 to be the same and just equal to the volume, you're going to get the maximal volume observable. We saw that if I take F2 to be that volume of the top plus the volume of the bottom plus the volume in between and extremize that and take F1 to be the action in the limit that these alpha plus and minus go to 0, we saw that that was giving the action of the Wheeler-DeWitt patch. We could also take both observables to be the space-time volume, and in the limit alpha plus and minus go to 0, the two contributions from the top and the bottom drop out, and we just get the volume of the Wheeler-DeWitt patch. That was sort of complexity equals volume 2.0. So I would say that we're kind of naturally led to this suggestion that, okay, this infinite class of observables we've written down in principle could be all good measures of holographic complexity. So if you take F1 to be anything, F2 equals anything, then you get complexity equals anything squared in these two guys here. So yeah, so these F12 observables should generically yield good measures of holographic complexity.
So these anythings and anythings you're talking about, you mean just like arbitrary D form and D minus 1 forms, or K forms?
Basically, yeah, just kind of any functional that you want to write down.
Anything can integrate on these K-dimensional surfaces. So
yeah, so I mean, it's not, okay, there's like some basic consistency conditions. Complexity like should be positive, okay? So this F12 observable, you probably don't want, you kind of don't want the alphas that you plug in there to be negative. You can definitely write that down and you get these sort of crescent shapes as opposed to the lens type shapes.
Right.
And those you can't guarantee are positive, for example. So, I mean, there's definitely consistency conditions, but there's sort of broad classes of sort of, you know, infinitely many things that are going to work as good complexity measures.
I mean, are they going to grow monotonically in time?
Yeah. This is great. You just lead me into that. Okay, so yeah, there's sort of two checks that you want to see. So the first one is this linear growth at late time in thermal states. So you can pick one of these complexity functionals, and we want to compute the time derivative and see that it has linear growth at late time with a growth rate somehow proportional to the mass of the black hole. So you can set up a planar ADS eternal black hole with this Eddington-Finkelstein-like metric. And basically, okay, we'll just take the example observable where we take the volume plus something like Peierls squared times a parameter lambda. Okay, so we're going to be extremizing this, and so we're going to need some surface. There's enough symmetry in this problem that we can just parameterize that as by giving the V and R coordinates as a function of sort of a radial parameter on the surface sigma. And so you can evaluate this functional in this background. And it's given by this equation where dot is equal to the derivative with respect to sigma. And so extremizing this is basically just a classical mechanics problems now. And all of the information about what observable you wrote down is just going to be contained in this function here that we call A of R. So depending on what invariant you write down, you'll get a slightly different functional of R, but otherwise this function will be the same in this background. Yeah, and so this is just, again, a classical mechanics problem for the functions V and R. You can reduce the equations of motion to just an effective potential problem. So this U of R is determined by that function A of R that I wrote down. So ultimately the potential is determined by which curvature functional we wrote down. And then this PV is like a momentum of this functional with respect to the V dot. Yeah, and you can see this action's independent of V. So this is going to be a conserved momentum in the problem. So this basically reduces it to a one-dimensional problem here. Yeah, okay, so here's kind of an example effective potential, and sort of the trajectories that go in and out are going to be, I don't know, that's going to be describing sort of just the radial, kind of describe sort of the radial profile of the surface. And so at the turning point is when you hit the potential, and then it'll come back out over on the other side like that. And so then you want to be able to evaluate. So this PV is determined sort of by the boundary time where you're anchoring the surface, and you want to evaluate how this thing is changing in time. So the functional, this is sort of a Hamilton-Jacobi-like relation, that the change in the functional, which is the complexity here, is going to be given by PV, which is like the Hamiltonian with respect to this time translation. Yeah, and so you can show at late times this PV kind of approaches this critical point where you have the maximum in the potential. And so at late times it approaches this P infinity there. And then this equation says, since PV is becoming constant there, that it's going to grow linearly in time. And when you evaluate the potential at that late time, you get that it's going something like m squared. So you get the linear growth proportional to n. Yeah, so this was sort of, I set it up in terms of a particular functional, but you can show pretty generically that you always have this behavior as long as there's some maximum like this in the effective potential. You're going to get this linear growth at late times. It is interesting though, for generic functionals, you will get this structure here where you can have multiple solutions. You could have some sort of bound states here. So those are going to be things that are maybe like running into the singularity, or not even that. They're sort of forming sort of weird, I think like kink-like sort of solutions in the middle there. So this is a situation where you could have multiple saddles, as you mentioned. So it's sort of an interesting question, but in principle, there's always going to be sort of an outermost maximal one that you want to focus on.
For general potential, are you guaranteed that the derivative of C is positive at all times? Because you said that at late times it becomes that m squared for generic, right? But are you guaranteed that
it's positive for all times?
Yeah, isn't that the case in the case of this two-bounded? Am I wrong about this? I thought that you just pull this up constantly.
Well, like the volume, I think probably is, but I don't think
the volume,
like things like the action. I think it's not right.
No?
Okay. I think it kind of has this transient behavior, and then it starts growing. So I think for some, yeah. So sometimes.
Because from the point of complexity, that sounds weird because it means that there's the Hamiltonian. There's a time that if you go further, you could have gotten that point faster, right? There's a shortcut.
Yeah.
This is like.
So I think, yeah, you have to, the point is though that those are usually short time scales at which those things happen. Whereas the linear growth comes at much longer time scales. So
the RT surface, however, is the volume of this, sorry, not RT, the volume of the maximum.
I'm pretty sure that one just increases.
Yeah, that increases just on the top.
Yeah.
All right. But sorry, if you did impose that this PV is positive, you still have a large class of.
Yeah, it's just like you're going to generic, like you might cut down some certain parameter spaces. I think if you have like large coefficients in front of your higher curvature things, you can get weird things to happen. But there's probably some sort of open set of parameters that things are going to be sensible measures of complexity.
Also, another question here, when you say late time compared to what, like, so there are two competing effects, right?
I guess there's some, yeah, there's
the time scale that beyond which becomes late is set by what parameter? Your potential? Is it your potential that decided, right? What is late?
I mean, it's going to be related to M, so either like a scrambling time or time scales that are even polynomial in M. I don't know. I think, yeah, probably scrambling though. There's not like a lot of I think we could, since we're kind of out of time, I'll just mention this switchback effect. So the second check that we looked at for these observables is that they satisfy the switchback effect. That's this idea that if you sort of evolve forward, backwards in time and start inserting operators sort of of the state, there's a specific behavior that you expect for the complexity, because if you go forward and backwards in time without inserting anything, these time folds should just cancel out. So it shouldn't really change the complexity. But then as you insert these operators, it should change the complexity related to the total length in between the insertions, up to a small correction that comes from the amount of time it takes for your perturbation to spread to the whole thing. So when you initially insert an operator, there should be cancellations of time evolution far away, and then eventually the effect will spread to the whole system, and then the cancellation will be complete. So holographically, you check this by computing these shockwave geometries where you sort of are gluing black holes of different masses together along these shockwaves. And roughly the switchback effect happens for these observables I wrote down for the same reason it happens for the volume. They're essentially additive in the length of this wormhole, and there's small corrections coming from the length that gives you something like this. And so you can check that these observables satisfy the switchback effect for the same reason the volume is. Okay, so yeah, just to summarize, so the goal of this talk was, on the one hand, we constructed an infinite class of diff-invariant observables using this relational construction and tried to argue that they're all good measures of holographic complexity, and they kind of hopefully reflect some of the ambiguities in defining holographic complexity. One of the things I found interesting about the problem is that this Peierls bracket construction can actually derive this extremality condition, and it enforces diff invariance on you. It kind of does it for free. And we verified that these observables satisfy two basic checks of measures of complexity, that they grow linearly at late times and they exhibit this switchback effect. So yeah, there's some future directions that are motivated by this. It'd be nice to try to derive a precise relation between these anything squared observables and things in the CFT. There's certain situations where you can start to do this for the volume. That was, again, in this New York Times paper by Bellin, Lukowicz, and Sorosi. And they used some of these canonical methods to start showing how you can derive, the transformation in the CFT and maybe what you're actually dual to in sort of, deriving the dictionary. It would be nice to maybe have additional criteria to, restrict maybe so it's not quite anything. So for example, things like positivity is a criterion that for measures of complexity. But there is a question of like, is there some other reason that volume is special in this whole construction? And there's some, if it is, what would be the analog of volume for other theories of gravity? So that's kind of an interesting question. And beyond that, I think this relational construction is actually quite useful for constructing observables in gravity. I think you can write down all sorts of interesting functionals. Okay, so Nima's question at the beginning, can you write down something that's localized in the bulk? Okay, the example I know here is that instead of doing the space-time volume and the codimension 1 surfaces, you just do a codimension 1 volume and the codimension 2 area boundary. If you write down that functional and say, okay, what's the extremization of that, you're going to get a constant mean curvature as opposed to a minimal surface. And that can be like a sphere in ADS. So you can write down functionals that are naturally extremized at localized subregions. And then you have this relational construction to write down all sorts of other things in those subregions as well.
That's different variance.
Yeah, it's defined dynamically by extremizing a functional. So,
That's so surprising.
Yeah, so that one I think is super interesting as a thing that people should start thinking about. So so in principle, you could start writing down things. There's the one caveat is
Constant curvature. constant curvature.
Yeah, it's like so in flat space, it's the spheres. Like spheres extremize this, and then this tells you kind of how to define a round sphere in curved space. You could define it as extremizing this thing. Okay, so yeah, I think there's all sorts of things that these observables are useful for. So anyways, I'll conclude there and take any more questions.
Thank you so much.
When the student today, we wrote some paper about when you are near the phase transition, the computer has a bigger the transition at the phase transition. Here it will translate into if you have ADS and deform ADS, the complexity of ADS is always bigger. With some assumptions.
Yeah, what kind of phase transition was it, or is the?
Well, that's a coronal phase transition. That's a critical point in, not in, I mean, like a phase transition. But if you do like try to do it holographically, you have the point of the transition is pure ADS, and if you deform away from ADS, well, if you deform from the transition point, you are like a deformed ADS, asymptotically ADS, but something different.
In the IR, or
yeah,
in the deep bulk, you get. Yeah. Is it like a change in cosmological constant, or is it just something?
No, you have to do some function of Z, suppose it's a real. You can write some metric here.
Okay.
And then the complexity, if you look at the volume, it's always bigger. Well, with some it's always bigger for the ADS, but some of the other descriptions we couldn't show that it's bigger.
You're saying ADS had the biggest.
Your ADS had, I mean, the
biggest
interpretation that you have long range correlation, so the complexity is larger because we have to get long range correlation. But for other prescriptions, we were not able to show. Well, maybe we were not very good at that. But might be good.
Yeah. Do you know these? I thought Netta Engelhardt had some papers related to volume and ADS, similarly trying to show that maybe that was maximal as well. Are you familiar with those papers? Okay. It sounds similar to that.
But, yeah. Okay, but the question is, the other prescription also is maximum complexity for ADS or not?
Yeah, I don't know. Yeah, it's probably a good.
Obvious, I think.
What does that mean in terms of, is there like a complexity reason for that to be true, or is it just happens to be true?
Well, no, but you have when you have the critical point, you have long range correlation. When you go away, you have correlation up to some length.
Oh, okay.
So you expect that creating long range correlation require more like local changes, so you expect the complexity to be larger, the larger the
I see. Okay. Length. I see. Okay. Okay. Yeah, that's nice. Okay.
Actually, can you arrange instead of some sort of RG flow from the UVCFD to the IRCFD holographically and see that complexity? Well, we saw for the volume, but we thought it was trivial. But then the other prescription is not trivial that is maximum. Yeah. So you can see and check. I don't know if you say something here.
Yeah, for sure.
Yeah.
So in the beginning, you mentioned that there is some ambiguity in defining complexity based on the reference state or the simple gates that you choose. And here you have the measure complexity.
Yeah.
So is there any correlation between like a particular system and a observer that might?
Yeah, I don't know. You would sort of need to be able to do this step to try to answer that question. I kind of hoped that somehow it was related to choices of simple gates somehow, just because, I don't know.
It's the volumes one measure that you define does not work as expected if you, for some particular reference state.
Well, wait, it doesn't work for. Sorry, why wouldn't it work? What would go wrong? I mean, you could write down a reference state that it would start decreasing the complexity, I guess. I don't know, or yeah, but I don't know. Yeah, for some reason, I feel like the reference state. Well, okay, it would be good to see if you could see what part of the construction is related to reference state and which part is related to choice of gates.
I think they should go hand in hand. If you say local gates, then your reference state should not have much non-local, long range entanglement. Because the goal is that this local things will generate the whatever basis your state is sort of factorized or almost short range entangled, you pick local operators in that basis. This is not a very sharp answer to what you said, but that's a qualitative.
Is there any?
Oh, okay. You usually don't pick like the vacuum state as your reference
You don't
state.
have to. If you just care about asymptotic growth, you don't have to.
So, I mean, in the class of observables that you mentioned, can you see explicit dependence on state or something?
We haven't really developed, I think, any part of that dictionary so much. I mean, the reference state, I think for us is always like the thermal field double state somehow. It's just like, yeah, we're computing the complexity relative to that when we're talking about this linear growth and stuff. So.
I also have another question. So this stuff that you said about the constant curvature in curved space, this sort of sounds superficially similar to what Yao has been trying to do. Maybe it was trying to do 10 years ago. It was trying to define quasi-local mass in GR. And the way he was defining it was in terms of consider a surface and all embeddings of this surface in some sort of curved geometry. There was some sort of funky prescription.
I've always found that.
Are you familiar with that story?
Roughly, but yeah, I think they're concerned about kind of subtracting. They're worried about like the 0 point. Yeah, I mean, it comes up here.
But they have different variant quantities at the end of
yeah, but I guess it always felt a little too complicated what they were doing to me. But somehow it's almost like I would say their problem is they want to compare their surface and curved space-time. They want to subtract off the value in Minkowski space. And the question is which value. Right. So they do this extremization procedure over embeddings. But you could just do this kind of thing instead. You say, okay, it's the ball. I don't know. It's the thing that extremizes this functional.
I guess
they.
I was hoping that this is secretly that complicated construction.
Okay, I would have guessed it's not, but I'm not sure. Yeah. All I have to related to that is we had some. There was a paper I wrote with Ted and Jose Senovia, kind of thinking about these kind of ball-shaped regions and various prescriptions for areas and volumes, and everything gets very complicated when you're working to second order, and you have to really think about shapes of things. And but this prescription for this CMC thing ended up coming out of that as an interesting, nice way of defining a ball. But yeah, the Yao thing, I think the other thing that is weird about the Yao thing is I don't think it works in higher dimensions.
Oh, really?
Yeah, because they're trying to solve some embedding equation that you just know doesn't have solutions in higher dimensions. Like, because they want isometric embeddings and it works in 4D, but in general, it's hard to solve for isometric embeddings in flat space. And so that was the other thing is like, okay, but on the other hand, these types of functional extremization arguments, you can. In some sense, I would say we're extremizing probably a simpler functional than what they are. Maybe that's, I'd have to look in detail at it,
Any last questions? For Antony?
I have a question. So for the regarding the last question, future directions. So do you have any guess like how to construct algebra? So you have introduced you showed how to construct observables here, and like F1 and F2, and but you say you can take like different choices, like you can construct different Fs. So I guess those could correspond to different geometric objects. In that case, how do you define like multiplication or
Well, I guess here, probably I'm interested in the Poisson bracket algebra, but basically I think the idea is you pick one functional, you extremize that's your subregion, and now you have this way of writing down all of these other things that are essentially dressed to the subregion that you wrote down. And so now you can start asking questions about like, you know, is your area operator central in this algebra or things like that. And you can kind of see the effects of, depending on how you defined it, if it was just like, things like if I did an RT construction, that area operator is probably going to be central. But if I did one of these CMC constructions, you can start seeing the area operator not being central in that. And so I think there's kind of interesting things you can do with this.
Okay.
Yeah. But yeah, I think the algebra there, and I'm thinking again of the classical mechanics problem. So the basically Poisson brackets.
If they think there could be some quantization procedure you could apply?
Yeah. Well, I mean, in principle, if you know Poisson brackets, you kind of know the quantum theory. There's like a way of building up the deformation quantization. So there's, in principle, you could do it order by order in H bar once you know Poisson brackets. In practice, okay, it's maybe there's definitely subtleties, but you know, the Poisson bracket at least tells you a lot about the quantization.
Right. So in usual quantum mechanics, using quantization using Poisson brackets, you need to add you need to do complexification of your manifold, so that you can add the degrees of freedom.
Yeah, well, that's just that's saying you consider complex valued functions.
Okay.
I mean, the real valued functions are your Hermitian operators, so I don't know. That's
They start with a Lie algebra, right? It's like a Lie algebra.
I mean, the Poisson bracket defines the Lie algebra. Yeah. So.
So it might be different from what you're thinking. Maybe someone doing algebra and cross product. Might be. I'm not sure if that's something. No more questions. Let's thank Antony again. Thank you. This was a great talk.